Hello everybody, I'm Kent Mayhew, and this is part of New Thermodynamics, and this video is Rethinking Global Warming. We're going to put out a new perspective, a simple one, concerning global warming. We're going to question current models. Okay, so irreversible lost work is work lost into the surrounding atmosphere by expanding systems. Now this is explained in my website, www.newthermodynamics.com, also my books, and also in other videos or YouTube videos downloaded on this site, New Thermodynamics, okay? So the question becomes, can lost work fully explain the relatively rapid temperature increase that we witness here on Earth? So we got to realize that the solar insolation, which is the solar input, is such that in 1.5 hours our sun shines as much energy onto the Earth as we humans consume in a year. So it doesn't really seem like us humans really do much in comparison to the natural world. Okay. Now you got to realize that global warming concerns a couple degrees of rapid average unexplained temperature rise, with the Earth's average temperature being 288 degrees. So we're really roughly talking, like if you just put it in ratio form, 2 degrees over 288 degrees. Okay. And we want to compare this versus 1.5 hours of sun shining over 24 hours, 365 days every year. And you can see that there's a ratio of 1 to 40 if you compare the two. So the question really becomes, does man's influence upon our planet's thermal energy explain the 1/40th ratio that we just saw? Okay, I don't really know, but we're going to test a few theories. So the accepted guise is that it is man's creation of greenhouse gases which act as a thermal blanket, and this is the real cause of global warming, right? If men's energy influence is so small compared to the natural energy coming from the sun, then you need an explanation. So greenhouse gases have become the explanation. Okay, now you got to understand that the insolation, or the sun's solar rays, tend to be at a significantly shorter wavelength, higher energy, than the thermal energy that is re-radiated by earthbound molecules. So the earthbound molecules absorb the sun's radiation, and then it re-radiates that radiation at a lower frequency. So then there's going to be more photons. Okay, so greenhouse gases absorb infrared photons and radiate it back towards the Earth's surface, and thus maintaining the Earth's elevated temperature. The accepted greenhouse gases being water, carbon dioxide, nitrous, methane, and ozone. These gases all absorb various parts of the sun's blackbody radiation at various near-infrared frequencies, or if you prefer, near-infrared wavelengths. Figure 8.3 here shows it in terms of wavelengths, and you can see the various absorption points, okay, at various frequencies by the different greenhouse gases. What is important here is to realize that we're talking absorptions in the near-infrared. Now, is near-infrared truly thermal energy? Thermal infrared is. Near-infrared is sort of between thermal energy and visible light, right? And so the point being is thermal infrared, which is true thermal energy, starts at 3000, which is at the right-hand end of this figure in figure 8.3, and extends to 100,000 nanometers. So it goes all the way right, and it's basically a linear function. Let's consider greenhouse gases some more, okay? We stated that they absorb in the near-infrared frequencies, okay, or wavelengths. But heat is thermal infrared dominated. In our bodies, we emit around 9.4 microns, which is 9,400 nanometers. That is to the far right of this graph. The graph ends at 3000. Okay? So the point being is, if you're going to talk about the heat being absorbed and re-radiated by gases, there's something amiss if you're comparing the absorption in the near-infrared to the thermal infrared. Okay, we're going to rethink what our thermal blanket really consists of, okay? Now consider the diatomic gases, such as nitrogen and oxygen, that make up 90% of our atmosphere. It is wrongly accepted that diatomic gases do not contribute to the greenhouse effect. This makes no sense. I mean, based upon their abundance and the fact that all diatomic molecules have a vibrational energy, It means they absorb thermal energy. So they absorb and they re-radiate thermal energy. That's like any other polyatomic molecule, okay? So Earth's thermal blanket applies more to thermal infrared, probably, photons, rather than the near infrared absorption of by what's called the greenhouse gases, right? The point becomes that the vast majority of the Earth's atmosphere acts as a thermal blanket, right? And we should never limit this just to greenhouse gases. Okay, now to emphasize what we just talked about, I have rewritten kinetic theory, okay, and it better matches the empirical findings or data, right? And it's published in Progress in Physics, which is an online journal, and you can look at it in 2018 and 2017 when the two papers were published, and they're shown below. The point becomes that most of the air absorbs and re-radiates thermal energy, as I previously stated, and this is all described by kinetic theory, and it has been empirically confirmed whether you think about specific heats or the heat capacity of gases. Okay, so there is some sort of disconnect between the accepted ability of a gas to behave as a greenhouse gas, its absorption spectra in the near infrared, versus its heat capacity, which is really about the absorption of heat, which is in the thermal infrared or thermal infrared absorption. So let's drive the point home. I mean, if the absorption spectra in the near infrared clearly defines a gas's ability to absorb and re-radiate surrounding thermal energy, then air should have an abnormally low specific heat. But air's heat capacity is similar to other diatomic gases. Okay, it is accepted that the greenhouse gases add about 33 degrees K to our atmosphere's temperature, i.e. it would normally be at 255 K instead of 288. But this brings now the question, to what degree is this due to the whole atmosphere versus just the upper atmosphere's greenhouse gases? We must realize that global warming concerns temperatures near our Earth's surface. Okay, so if the total atmosphere acts as a thermal blanket, then obviously all global warming models need reconsideration, because they don't take into they do not realize that man's contribution to global warming is located on the Earth's surface. Hence, it must contribute more to global warming than the simple 140 argument that I presented earlier. Okay, so basically, we have to rethink what we're doing. And we can never forget that the sun's thermal energy contribution remains significant here on Earth, but it enters our atmosphere from outer space. And when it is absorbed by earthbound molecules, it is re-emitted radially as more abundant, lower energy photons. Now, we got to talk about the natural pressure-temperature relationship, okay? The new kinetic theory, as proposed by me, implies that intermolecular collisions are inelastic. Okay, so this means a few things. It means photons are given off during collisions, which means that the spectral irradiance, as measured here on the Earth's surface, may be strongly influenced by photons from such collisions. It must also be said that natural pressure-temperature relations influence the Earth temperature as witnessed here on the surface, right? You increase the Earth's pressure, it increases temperature. And the reason that this does so is that you increase the number of photons that are given off by collisions. Nikolov and Zeller put out some interesting papers recently. Okay, they have asserted that our witness temperature is actually a combination of the insolation, solar input, plus the pressure of our atmosphere, or as I call it, the natural PT relationship. It should be emphasized that neither classical thermodynamics or the sciences, nor Nikolov and Zeller realized why the natural pressure-temperature relationship exists. Okay, and again, I repeat, it is because of photons being a result of inelastic intermolecular collisions. And most of those photons are probably going to be thermal energy photons, okay, which means infrared. I mean, Figure 1 shows what we've been talking about, okay? And basically, you got to consider the Earth's atmosphere as a total thermal blanket, okay? So, I mean, we have black body radiation from our sun is absorbed and re-radiated in all directions. This occurs at all levels of the atmosphere, okay? And again, we repeat, the re-radiated energy is at a lower frequency or lower energy than the absorbed radiation use. Okay. Now, heat from the planet plus mankind's thermal input is similarly absorbed and re-radiated in all directions. Global warming concerns temperature increase near the Earth's surface. Okay, and increases temperature near the Earth's surface due to natural pressure temperature relations exist, right? But you still got to realize that man's contribution is at the surface. So what? I mean, the outer atmosphere has the greenhouse gases. Also has our ozone, which protects us, right? Ozone's a greenhouse gas too, okay? But the Earth's atmosphere is diatomically gas dominated. And diatomic gases also absorb and re-radiate thermal energy. So the Earth's atmosphere as a whole must act as a thermal blanket. Okay? Okay, so accepting that lost work by an expanding system is irreversible work onto the surrounding atmosphere, we now have irrefutable clarity that lost work ultimately heats your atmosphere. Okay, so you drive to the corner store, only put a relative amount of lost work into our atmosphere. But ask, what happens if 10 people do it, or even 100 million people do the same thing? Now lost work has the potential to become significant. Even so, it does not compare to the insulation our planet receives from our sun. However, as previously discussed, we've got to consider the location. Okay, on the Earth's surface, it becomes so much more relevant that lost work occurs on the Earth's surface. Okay, so especially realizing that our atmosphere as a whole acts as a thermal blanket, this changes the way we should think. I mean, so how does one calculate the energy the thermal energy that is given into the atmosphere when driving one's car? Considering all the motions and the lost energy, lost work involving the driving of a car, it seems like a horrendous task. However, the answer was probably simple. I mean, you assume that the car accelerates, hence increases its inertia, and this represents the energy required to accelerate the car's mass. After you reach your top speed, then all other energy goes directly into heating our atmosphere. So if you're driving along the highway at 60 miles per hour, then once you reach that speed, then all energy used to maintain that speed goes directly into heating our atmosphere. You can consider this as a combination of the drag plus the car's frictions plus lost work by the piston cylinders, expanding systems, piston cylinders. Heck, even the inertial energy, though, will eventually be turned into atmospheric heat when we apply the brakes. Okay, now I don't have all the answers, okay? I must state that there are doubts even in my mind to how much damage a moving car or even mankind as a whole does onto our atmosphere. But before any real conclusions can be had, the current models all need an overhaul. Until this is done, this author remains very doubtful that man's contribution to global warming does not include our activities, and this could be critical. Okay, we've got to change our thoughts to our activities rather than like greenhouse gases. Remember, every time we disturb the natural dynamics of our atmosphere in any way, shape, or form, then we're actually heating the atmosphere. And never forget, it is Earth's atmosphere, it's not ours. And I end the slideshow with discussing my book, New Thermodynamics, Say No to Entropy. I want to express that I'm rewriting it for the third time, namely because I've had some new insights, okay, and the new book will probably be called New Thermodynamics, Goodbye to the Second Law. The realizations have changed things like Chapter 4, so I'm sorry if anyone bought it. You can get Chapter 4 online from my website, www.newthermodynamics.com. Most of what I've discussed here is in my books and in my website. Okay, also on my website you'll find my peer-reviewed and other papers. I do apologize for my odd mistake, as they certainly exist, and I guess I'm really apologizing for being a human being. Okay, accordingly, any help and or improvements or commentary is always appreciated.